In our last lecture on Friday morning, I think we went as far as the factors that actually affect the splitting between the energy levels that are caused by a ligand field when the ligands bond to a transition metal. But perhaps before I finish off what I have in the slide that I have here, let me just quickly take you back that I've introduced a new method of bonding or a new mode of bonding that is called the crystal field theory, according to which a metal acts as a cation, a positively charged ion, and ligands, because they are bringing up electrons to make those bonds. They are essentially negative charges. And as a result, this bonding is interpreted as, an electrostatic type of interaction. Think of your Coulomb's law. And I've shown you the shapes of the orbit, the d orbitals, that their shapes are very important in determining how they interact with the incoming ligands. And you have seen that the spatial arrangement of these orbitals is such that two of the 5 d orbitals are aligned with the Cartesian axis. The Cartesian axis are your x-axis, y-axis, and your z-axis. So you've seen that there's one orbital that has got 4 lobes, and the four lobes are aligning with the x and the y-axis at the same time. So it means that orbital is able to take or to account for 4 ligands in an octahedral complex, a complex that is formed by 6 groups or 6 ligands or 6 donor atoms coming towards the metal to form bonds. And the one orbital perpendicular to the plane of the x and the y-axis, which is your z-axis, or the orbital along the z-axis, the dz squared, that is taking care of 2 ligands. So you've got a total of 6 ligands in an octahedron. This is why it's simple when discussing this theory to start with an octahedron, because students can actually be able to see the direction of approach of the ligands as they bind to this transition metal. So that is a very important thing, and it had consequences where we found that the d orbitals, because the 5 of them have got equal energies when the metal is not bonded to anything, but in the presence of a ligand field, when ligands come to bind to the metal, then the degeneracy or the equi-energetic state of the 5d orbitals breaks down, and you've got sets now of orbitals, 3 orbitals being lowered in energy. That is because they are not pointing towards, their electrons are not interacting or repelling the ligand electrons significantly, because the ligands are far away from those orbitals. So they are lowered in energy. But we have seen that the orbitals, the ligands that are coming along the x and the y-axis, interact strongly with the dx squared minus y squared orbital. And as a result, that orbital is going to be elevated in energy because the repulsions will be high. And we have seen that the second or the other electron ligands coming on the z-axis interact with the dz squared and cause that orbital to be elevated in energy. So the 2 orbitals that are now forming a degenerate set will be the dx squared minus y squared and the dz squared, which are forming the high energy orbitals in an octahedron. That degeneracy of all the 5 orbitals being equal is no longer there, and the 3 orbitals have now gone down in energy. That is very important, because now electrons, as opposed to what you're having in a normal metal ion, where the electrons will occupy all the 5 d orbitals one after the other, not pairing until all the 5 orbitals have been occupied. But now if you're looking at an octahedron, the electrons will now start occupying the 3 orbitals that you have in a T2G orbitals before they go to the EG, because there's an energy separation that the electrons have to defeat, if you want, or to overcome in order to get to the high energy state, or the EG state. So that energy, which we called delta O for split change in an octahedron complex, or 10dq, is very important in determining or answering one of the questions one of the students asked, that I just see being spoken of the D4 electron configuration. That D4 electron configuration is determined by the charge on the metal ion, that you are left with 4 metal electrons in that and those electrons will have to occupy the orbitals that you have in that particular octahedral complex. You've got that metal ion at the center, and the electrons, the 4 electrons, depending on the strength of the ligand field, either weak or strong. Strong field ligands, I said, they cause very large splittings. The delta O is so big that electrons cannot afford to overcome it, to cross it and go to the high energy state. And as a result, in a strong field case, the electrons will populate the T2G orbitals until it is fully occupied before any electron can go to occupy the EG. I think that partially answers the question that one of the students asked, that why do you have a D4 in the weak field case, having 3 electrons occupying the T2G and 1 going to the EG? The reason is that the splitting in a weak field, the delta O, is so small compared to the amount of energy that you need to put electrons together in the same orbital, which is called the pairing energy. So because the pairing energy is large, electrons can afford to easily get into the high energy orbitals, which is the EG set. And as a result, before the T2G is completely filled with paired electrons, the electrons do not pair, but any available electron goes to the EG set. And this is why you saw the 4th electron in a weak field case go into the EG orbitals. That is, well, the question may be good for other students to get in, but I think I had explained the interplay between the size of the delta O and the pairing energy. That now in a strong field case, we're having a very huge energy gap now. The delta O is so large that electrons cannot overcome. They not prefer going up. They will prefer pairing up because that energy is larger than the pairing energy. But once the T2G is completely filled, any remaining electron has got no choice, because you can't have 3 electrons in an orbit. So it has got no choice but to go to the high energy state. But that is why in the case of the D4, you don't have any electron that can go up to the EG in a strong field, because all the electrons can be accommodated. A total of 6 electrons is needed. So I discussed with you enough factors, and I've shown you the importance, how you can get the delta O. You run a spectrum of your coordination compound, and you look at the highest peak in the spectrum and look at the corresponding value of the wavelength or the frequency on your abscissa or on your x-axis, and use that to calculate the splitting energy or delta O. And I said that you definitely need, having identified that wavelength, or you can use the Planck equation to calculate there. So that is very easy. And I said one of the consequences that I think I discussed with you on Friday was that depending on the size of the splitting, you've got different colors coming out from different compounds, because they are actually absorbing different energies of the electromagnetic spectrum that is governed by their delta O. So the colors of the complexes depend on the size of the splitting that has happened in the d orbitals of their metal centers. And the color that you see is actually a complement of what has been absorbed. And I showed you the color wheel that will allow you to predict which color is going to be given off when another color is absorbed. And those, I said, those are called complementary colors. Because if you take the color that is absorbed and add it to the color that is transmitted, that you see with your eye, if you combine them, you get back to the original light that you've shown onto the complex in your analysis. That was one of the main aspects that I think you'll need to familiarize yourself with. And then I discussed the factors that influence how big the separation is. That has been, ligands have been identified as one of the factors. The metal ion itself, where it is in the periodic table, has been another factor. And the charge or the oxidation state, you've seen that if your complex has got a metal ion in a very high oxidation state, then it will interact with the ligand significantly, so that the delta O becomes too large. And if you've got a small charge, then the interaction with the ligands will be minimal, and as a result, you get small. And that's a very important thing in mind, and be able to rationalize the observation. And the last thing that I discussed with you is where I am today, that the number of ligands that are bonded to it or that are bonding to a transition metal center also determine the extent to which the splitting is going to happen. If you've got many ligands that are bonding, they'll definitely cause a larger effect on the metal ion and fewer ligands. For example, in this case here, or in your textbook, you'll see a comparison between an octahedral environment and which has got 6 ligands, and you've got a tetrahedral environment which has got 4 ligands. So essentially, the amount of splitting that is caused by 6 ligands always exceeds the amount of splitting that is caused by 4 ligands. So essentially, all tetrahedral complexes will definitely have a high spin because their splitting is very small. You can see I've written it at the top there. Let me say, at that point there, I've indicated that the delta O for an octahedron is twice as much as it is in a tetrahedron, because you've got 4 ligands in a tetrahedron. So that will be a smaller fraction of what you have. And that has got consequences. As a result, you can see the last column that I have, or the last value in the column on the table, that I really, if you are to calculate the value of delta for the same ligands, if you've got 6 ligands of, say, the chlorides bonded to a metal ion, and you've got 4 ligands for the same metal ion, then the amount of splitting that will happen in a tetrahedron will be 4/9 of the delta O that you gave to. So if you are given, say, the splitting amount in an octahedral complex, and you've got a similar tetrahedral complex, then you must know that that's going to be a fraction. The splitting will be a fraction, 4/9 of that value. This is what I talked to you guys about on Friday, and I thought I should just say something about it, which is what I'm doing now. Before I take you really, perhaps the octahedron, the tetrahedron thing came, but it's a must because I was discussing the number of ligands and the shape of the molecular geometry, if you like, as a factor that affects this. But you can see it clearly in the next slide that what really happens when you've got 4 ligands forming a tetrahedron, which is sort of a sub-fraction. It's a smaller symmetric figure than an octahedron. You've seen in an octahedron that your ligands are very directed. The bonds are directly coming along the X, the Y, and the Z axis when ligands and metal ions bond. But in an octahedron, we will see a different conformation because the tetrahedron is not as symmetric as the octahedron is. And let us look at how the splitting pattern changes as opposed to what we've seen in an octahedron, where 3 orbitals, the T2G, or 3 orbitals which were not pointing or which are not aligned with the axis are lowered in energy, and 2 that are aligned with the axis are elevated as a result of interaction with a ligand field. Now we've got a ligand field that has got a shape of a tetrahedron. It's your polyhedrons in your maths, right? So we've got a metal sitting at the center and the ligands arranged in the form of a tetrahedron. So this is how the splitting is going to happen. Perhaps it's in the next slide and not this one. This is another very important slide here, or information that you need to be familiar with and be able to apply. It is on the determination again of the splitting parameter. That is the energy gap between the T2G and your EG set of orbitals. It is empirically derived, and values have been determined, and they are tabled in textbooks, and they've been tabled by this guy called Jorgensen, and they are essentially known as Jorgensen parameters. They are used, you can use them directly without going into recording the spectrum. You look at your metal ion and you look at its corresponding feature or parameter in the Jorgensen series, and you take that and you look at the ligand under consideration in that complex, and you essentially doing a multiplication. So you can see that the splitting energy in an octahedron can be calculated by taking up a product of the F parameter, which is a characteristic of a ligand, and the G parameter, which is a characteristic of a metal ion. So in your table, in the tables, in the textbooks or in your references, you will find the G values for the metal ions, and you'll find F values for the different ligands. And you're seeing that the units are essentially a bit stranger thing to you, but I think from now onwards, you will know the units of energy that you haven't known in spectroscopy. We're using the unit called a kilokasar. A kilokasar. Kilograms came to the thousand or something. So a kilokasar is a unit that represents 1,000 wave numbers. So because your answers are coming up as wave numbers in your spectroscopy, so you can easily convert those answers to kilokasars if you like. So the G values and this is just a warning that you don't need to memorize these values. In a case where me and my colleague in the course are going to ask you a question on this system, we're going to give you these values here. And the important thing is we can get values from spectroscopy that are given off, and we give you the values of G and F for the same complex, and we ask you whether a complex would be high spin or low spin. What you need to do will just be to compare the product of this as your delta O and the pairing energy, and you can decide from there if pairing energy is larger or the pairing energy is lower. That's the criterion. So please just familiarize. I think I've got some previous question papers that ask such a question. So you can look at that and work through them. If you're uncertain, just give us a buzz. Unfortunately, I'm rejected on the WhatsApp, but my colleague is connected on WhatsApp, so you can even send WhatsApp messages. He is going to call me to sit down, and then we carve out a way of addressing your problem. So please continue communicating and continue communicating with the slides as well. Right, let us now go to the slide that I wanted to talk about when I was looking at the factors that affect or influence the splitting energy, or delta O. And you can see in the plot there, that is your energy. You've got your, at the bottom, you're having your unperturbed d-orbitals. But in the presence of a tetrahedral ligand field, the tetrahedral ligand field will split now the d-orbitals in this fashion here. Doesn't want that. Fine. Something is up there. In there. And register. Okay, in any case, look at the cycled part there. Apologies once again for the disconnection. It's wave of the internet connectivity here. But importantly, I wanted you to see the difference between an octahedron and a tetrahedron. In a octahedron, you have seen that the ligands are coming along the X, the Y, and the Z axis. But in the case of a tetrahedron, look at the balls that are on the cube there. Do you see the cube, or all these structures are cubic in any case? In an octahedron, you have got a ligand that is not in any of the axes. It doesn't come along any of the axes. You can see the filled balls which look black there if you want to look at them. If you want to consider the hashed ones, the hashed ones are supposed to be deleted in any case with the way it is here. Because the fourth black ball is hidden by it's somewhere beyond the origin. It's hidden by the cluster of orbitals that we have here. So what we're looking at, what we're seeing is that in a tetrahedron, the ligands approach in between the axes rather than along the axis. And as they do that, as they bond to the metal through those directions, they interact significantly with those orbitals, those d-orbitals that are not aligned with the axis. And we have said that those are the dxy, the dxz, and the dyz. Those are actually the orbitals pointing into the spaces between the Cartesian axis. And in a tetrahedral ligand, and those constitute what we call the T2G set. So in the case of an octahedron, we see that those are the orbitals that are mostly involved in the bonding rather than the ones that are aligned with the axis. And as a result, significant repulsions happen with the orbitals that are in between the axis. That is the T2G, if you like. Those are the ones that are hit hard by a tetrahedral ligand field. And as a result, it elevates the energy of the three orbitals and lowers the energy of the two orbitals along the axis. Now you can see this is an inverse splitting. You're seeing an inverse oh no, problem here. Right. I'm getting stuck on this here, but I think I've been able to draw your attention to the fact that the splitting pattern that happens in an octahedron is essentially different from that happens in an octahedron. Is the opposite of that. You can see the two orbitals are now at the lower end, and the three orbitals are now at the higher end. So it's actually an inverse of what the splitting that you've seen in an octahedron. And another very important thing that I would like you to realize is that if you look at an octahedron itself, say you're considering the black balls on this cube here, there's no way that you can manipulate or carry out symmetry operations at the center in such a way that you will bring that into a negative of itself somewhere, or take that into a negative of itself. So the octahedron doesn't have the center of symmetry in symmetry terms. And as a result, because it doesn't have an inversion center or the center of symmetry, it's not even with respect to inversion. You're getting a different figure. Because if you are to reflect, say you have to reflect this ball along the XY plane, it's going to come down here. And if you reflect in that ball, it's going to come down here. And if you reflect this, it's going to go up there. So it will be a different conformation from what you have seen. And as a result, we're saying a tetrahedron is not centrosymmetric. It's not even with respect to inversion. And as a result, it's not gerade. So you look at the term labels that we have here, they do not have the G subscript. That G subscript has been taken off because of the lack of symmetry inside this tetrahedron here. So we've got the same, the three orbitals that are designated T and two that are designated E, but they do not have the qualifiers, the G qualifiers that we have seen. That is because of the fact that the geometry that we're looking at and the tetrahedron doesn't have a center of symmetry, or it's not centrosymmetric. That is very important. And another very important thing is that the splitting energy or the gap between the T2G and the EG is now called delta T. Remember, we had delta O for an octahedral arrangement of ligands or for an octahedral complex. Now that we've got a tetrahedral complex, the splitting should be characteristic of that complex, which is now our delta T, if you look at it on the right-hand side of that particular diagram there, I've designated it as delta T, which is the splitting between the T2G and the EG set. And because delta T is caused by 4 ligands, it is actually smaller than the same splitting that is caused by 6 ligands, the same ligands with the same metal, but if the ligands are increased to 4, we've seen you will get double the amount of the splitting. And as a result of the small splitting in tetrahedral environment, all your tetrahedral complexes would be high spin. They don't prefer pairing because electrons can easily access the T2G. You have got one electron occupying any of these and the second one, so there will be 2, as opposed to what we've seen in an octahedron where 3 would be a trivial case, that 3 electrons can be packed in a T2G set in accordance with Hund's rule. But now it's 2 orbitals at the bottom or lower energy orbitals, and 2 electrons have to do that, 1 there, 1 here, and the rest would go up there. So if you've got electron configuration up to D5, those electrons will be distributed singly in both the EG and the T2G before they can start pairing. That is because of the small splitting relative to the pairing energy, if you like. And as a result, these complexes will prefer to be high spin. They are always high spin, as per the statement at the bottom there. Keep track of that. This is because you've got fewer ligands and they are essentially weak field in any case. Tetrahedral complexes are formed from weak field ligands. As we go into distortions, you will see that we can have a sister geometry to a tetrahedron. These shapes are not new to you, the molecular shapes. They have been introduced to you in the SCHM012 course under the valence shell electron pair repulsion theory. But, all these shapes that I'm talking about are not new things. You've actually seen them and you can visualize them and agree with the deductions that are coming through here. Okay, so now just a contrast between the 2 geometries here, which is very important. In an octahedron, you've got 6 bonds, and in a tetrahedron, you've got 4 bonds. And energetically, 6 bonds favor, or 6 ligands actually favor the octahedron, when the 4 favor the tetrahedron. And if you look at the second, very important issue comes up in the second point that I have there, that in the case of ligands, have got different sizes. I think at some point we'll have a small section that is dedicated to looking at the ligand size. But from your organic chemistry, you've studied steric hindrance, that if you've got bulky groups sitting closer to each other, they will prefer a different conformation in order to reach stability. So we also in inorganic chemistry have got such that the center is one. You've got one central metal and you've got a number of ligands coming through bonding to that metal. And the size of the ligands will be very important, because if you've got small sized ligands, then you can accommodate as many as possible. As many as possible. I'm not saying infinitely many ligands. You can, as many as possible can be accommodated around the same metal center. But if the ligands are big, definitely they will push each other out of the coordination sphere of the particular transition metal, and only few will remain attached. And as a consequence, you can see that big ligands in this case would favor a lower geometry, which is a tetrahedron. That is because the tetrahedron also has room, for such. Because if you look at, I think, remembering back to your first year, which I've just highlighted, the valence shell electron pair repulsion theory and molecular theory, you know that the electrons in a tetrahedron, or say in an octahedron, the bonds would be at 90 degrees away from each other. So you've got a 90-degree separation between adjacent groups that are bonding to the same center. But in a tetrahedron, the groups that you have, the four groups, will, between adjacent groups, you'll have 109 degrees. 109 degrees is a bigger angle, and it will favor larger ligands. So because the octahedron is confined to 90 degrees, bigger ligands cannot be accommodated within that space. You can argue it from that or understand it from there that large ligands will favor a geometry that makes room through the bond angles, if you like. And the crystal field stabilization energy obviously will favor the octahedrons rather than tetrahedrons, because we've just seen that tetrahedrons are high spin. The electrons do not, repel each other that much because they are having single spins in separate spaces. They occupy different regions of space. And as a result, we said tetrahedral complexes are always very energetically favorable, and it is one of the consequences of your Jahn's rules that for degenerate orbitals, you need to have electrons occupying them one by one. Another very important energetics-related phenomenon is what is called the octahedral site stabilization energy. There are different sites, as we will leave. I think we will come across such again at when we treat the concept of spinels, that you can have the same metal or different metals in different coordination states or different coordination environments. So a metal or a particular oxidation state of a metal will have different tendencies to choose between different coordination environments. So if you've got a system that allows both tetrahedral coordination and octahedral coordination, and you've got a metal that is somewhere in a +3 or +4, these oxidation states will preferentially go to specific coordination sites. And this is what is at play here. The octahedral site stabilization energy means that is the energy that makes ligands to prefer the metals. To say, if you look at spinels, it will be a metal preferring to occupy octahedral voids. Those who are doing geometry, the geology will remember this, the concept of spinels or metal oxides in geology, that there will be different, because of the different sightings, the metals will be into, because the spinels can be considered as a close-packed arrangement of oxides or spheres that are oxides in nature, and the metal will then go into the voids that are, because balls do not just close up, they will leave gaps in between, and those gaps are essentially coordination sites, if you like. And the energy that favors a particular oxidation state residing in either in the octahedron, in this case, favoring the octahedral site occupation rather than the tetrahedron, it's called the octahedral site stabilization energy. So the metal targets, or the particular oxidation state of the metal targets the octahedral site in a particular system. We'll see this when we get to the spinels very soon. And we have just seen in the previous splitting pattern that the splitting that is caused by 6 identical ligands on the same metal ion is twice the amount of splitting that is caused by 4 of those ligands with the same metal ion. So the splitting that you have in a tetrahedron is about half, if you like, of what you have in the octahedron. So 6 ligands or 4 ligands will cause half the splitting that 6 ligands cause on the same metal ion. The other very important thing is the high oxidation state. It favors many ligands. It can pull as, because the oxidation state is the positive charge that you're having on the metal, and positive charges like negative charges. So it can pull as many negative charges as possible. This is why you're finding that most of the coordination compounds where the metals are in high oxidation state are actually octahedral rather than, because, and we have discussed this part over here. If you look at I think I've indicated the concept of the splitting. The splitting, my space here doesn't allow me. Right, but in an octahedron, there is very large splitting. We've seen this in factors affecting 10dq or the delta O. That because of the large splitting, octahedral complexes will be favored by the high oxidation state as such. So that's an important point I wanted to raise here. I said that what I was saying about the octahedral site stabilization energy pertains to a class of compounds that can be found in geology, which maybe you are spinels here. The spinel is actually a name of a compound, a geological compound, magnesium aluminum oxide, if you like, or magnesium aluminate. Its structure is a combination of different geometries. If you look at the different metal, the balls that you're having inside here are all metal ions. And the geometries that you're seeing, the pink, the pinkish or whatever color that is, the bluish, those represents the oxides, which are ligands in this case here. You've got 2 metals and you've got the oxides that are making up the valencies. So obviously you've got the brown balls that are so big and the silver ones that are very small, and that can also, you can deduce which one is which by referring back to your periodicity in your SCHM012. That you have seen that in your periodicity, ionization of an element causes difference in sizes. If you lose electrons, then the resulting ion becomes smaller than the parent. And if you lose or you gain electrons, then the resulting ion becomes bigger. That is one of the periodic trends that you have learned in your previous years. And the important thing is the larger one here would definitely be magnesium, because magnesium, though it's in the same row or in the same period as aluminium, it has got a 2+ oxidation or 2+ charge, and aluminium has a 3+ charge. So obviously that will give a small. So you can see that if you look at the pinkish connections, a metal and 6 coordination environments, if you like, that sort of gives you a tetrahedron. And you see that if you look at the yellow balls, bigger balls, which are magnesium, you can see a tetrahedron being defined around them, if you like. And as a consequence, magnesium would be residing in a normal, this is a non-transition metal. The name Spinel was realized a long time ago when by mineralogists, and they actually gave this structure or this name Spinel, but then it was extended because of the similarity in the type of compounds that transition metal form. So importantly here, what I would like to realize is that you've got both tetrahedral sites and octahedral sites in the same compound, if you like. And as a result, the different oxidation states will prefer sitting in different sites. And this is a very important point where the crystal field theory comes in as a very handy criterion or tool to deduce whether the particular ion will go into an octahedral environment or will go into a tetrahedral environment. So this is because of the similarity between the metal oxides of transition metals and the mineral spinel itself. and they are different. They are given by a general formula for spinels. You have got a formula A, B, two of the B. You've got one entity of an A type of, it's a type of metal ion that you have. It's an A type and a B type. So the A type metal ion will be the one that is in a tetrahedral environment surrounded by 4 oxide groups in this case, if you like. And the B2 or the B will be a type of spinel atom that is in an octahedral environment of the oxides as well. So you've got the one is under the influence of 6 ligands and the other is under the influence of 4 ligands. Then that distinguishes the different sides that you have. So metals have got different energetics to go into those sides as such. And let us just put things into perspective. The spinels or mineral spinels are classified into 2 divisions or 2 categories. You have got what is called a normal spinel, and you've got what is called an inverse spinel. They are all spinels having the same molecular constitution, if you like, or atomic constitution, but the arrangement or the siting coming from the octahedral site stabilization energy that I spoke about. Right? You have got in a normal spinel, the metal in a 2+ oxidation state will occupy tetrahedral sites. So if someone asks you to define what a normal spinel is, this is something that you can say that a normal spinel is a type of spinel where metals in a divalent oxidation state occupy tetrahedral sites, and those in a 3+ oxidation state or in a triple oxidation state occupy octahedral sites. And you can designate that as a formula down here. You can see that at the bottom here, I have got a metal ion. I've got this metal ion in a 2+ oxidation state that is sitting up in octahedral environment, tetrahedral environment of the oxides. The ligands in a spinel are oxides, oxygen 2- or O2-. So that is the ligand environment you have in there. And the B2 is designated by this M, and M is just M2. This guy could have put it as M2. So you can see that in the octahedral sites, you have got the metal in a 3+ oxidation state. So such a siting, such a designation tells you that the spinel under consideration is normal. But in a case where you've got a redistribution of the ions, then a different conformation comes up. If you find that the 3+ oxidation state that we normally encounter in an octahedral environment is now occupying a tetrahedral site, then we're talking about an inverse spinel. That is what you're seeing at the bottom here. That of the 2, this is supposed to be your M2, which is the B type of atom in a 3+ oxidation state. Half of that is now redistributed and is happy in the tetrahedral sites. So intrinsically, naturally, the M3 has to occupy octahedral sites. But in this case, the energetics favor it to go out into the tetrahedral environment and promote the tetrahedral environment or the divalent ion into the octahedral site. So you can see that half of these elements have been distributed. Half of the 3+ is now taken out to be in tetrahedral sites, and the remaining half is paired with the divalent. So this constitutes an inverse spinel. And you can easily use crystal field theory terms to distinguish between this, or to decide which type of spinel or where each ion is going to go. You can do that by way of the crystal field theory, and I will demonstrate that with progression into this. Just to put things into context here, that spinels are represented by the AB2O4 formula, and they can be normal or inverse spinels. and that is dependent on the sightings of the different oxidation states of the metal ions in that spinel. It's going to be normal if entirely the divalent oxidation state resides in a tetrahedral environment, and the octahedral, the 3 plus resides in the octahedral sites. So you can see I've got many examples of spinels here, but there are so many as well. And the crystal field stabilization energy, which we defined in our previous lecture as the energy that is dictated by the distribution of electrons in the splitted d orbitals, is a very important tool or criterion that one can use to decide if a given spinel or if a particular spinel is normal or is inverse. It has got a normal structure or it has got an inverse structure. And we said it has got a normal structure if the divalent is in the tetrahedron, trivalent in the octahedral side. But its inverse is 50% of the 3 plus oxidation state is now in the tetrahedral side, when half of it remains in the octahedral side and the 2 plus joins it in the octahedral environment. That is where inverse now. So in order to use the crystal field stabilization energy as a criterion to decide on whether a given spinel will be inverse or will be normal in this mineralogy, that's Professor Dan Levy stuff and them. If the 3 plus oxidation state of a specific metal in a spinel has got a higher crystal field stabilization energy in the octahedral field, it means that it is preferring to be in the octahedral size because it is stabilized there. The stabilization energy that allows it to reside or to occupy those voids is actually favoring there. Then we say that it is a normal spinel because the energy, the crystal field stabilization energy of the 3 plus oxidation state is larger compared to that of the 2 plus oxidation state of the metal in that particular spinel, right? And now the spinel will be inverse if the opposite is the case. If the metal ion in a divalent state has got a larger crystal field stabilization energy than the 3 plus oxidation state, then you've got an inverse spinel. Right, I'd like you to keep that criterion in your head and use it towards answering questions or towards applications. For those of you who are doing geology, working with minerals, there's a lot, a variety of minerals that come up in or crystallize in this structure here. So that can be very handy for you guys. Let us look at how we can use the crystal field stabilization energy as a criterion to classify spinels as being normal structured or inverse structured. And taking the first example here as the spinel of manganese, which is a spinel in any case. The thing is, you can write that as magnesium or manganese oxide. How do I do that? Let's see if I can say. Whether it will allow me to do that, I don't know. But you can actually write this as it refuses. Okay. Right. So, but in any case, look at the example that I have. Example 1 is on the manganese oxide spinel. This comprises MnO and Mn2O3. So it's a combination of 2 oxides. MnO as manganese oxide. Or let me say manganese monooxide. And it's a combination of that and manganese trioxide, where you've got manganese, manganese, 2 of the manganese and 3 of the oxygen. So in the Mn2, you've got manganese in a 3 plus oxidation state, and in manganese monooxide, you've got manganese in a 2 plus oxidation state. That is what you're having down here. And very importantly, the ligands that you're having are oxides. And if you go back to the spectrochemical series that I discussed with you on Friday, you'll find the oxides being towards the low end of the spectrochemical series. And this is where I said that we'll be discussing or ironing out that shortcoming of the crystal field theory which is showing up as the spectrochemical series, the experimentally determined values of the splitting parameter of transition metal compounds as induced by the ligands. That is very important, and I would like you to keep track of that. So the oxides are the ligands, weak field, so you don't have any pairing preferentially happening here. So you've got manganese 2 plus as a component of that spinel, and you've got manganese 3 plus as a component of that spinel. So manganese is in both the 2 plus oxidation state and the 3 plus oxidation state. So you have to look at the energetics of it being found in, say, the octahedron, because if one doesn't happen in one, you know it's going to be the other, right? So considering that, manganese 2 plus, manganese is in group 7 of your periodic table, so manganese 2 plus will be a D5, because that's going to be 7 minus 2. You've got 5 D electrons, and if you subject those to an octahedral ligand field, you're splitting into the T2G. The D subshell splits into the T2G and the EG set. So you've got 3 orbitals T2G and 2 at the top of the EG, and you've got all the orbitals, because this is a weak field ligand. The electrons occupy the EG set even without complete occupation of the T2G. So all the orbitals will be singly occupied by electrons, because they're under the influence of a weak ligand field. So you've got 3 electrons taking up the T2G and the 2 electrons taking up the T2G. And then you work out the energetics. We said to calculate the crystal field stabilization energy, you look at the number of electrons that are in each of the orbitals. In the T2G, those orbitals are lowered by minus 0.4 delta O, and the EG are elevated or raised by 0.6 dq. So you just multiply the number of electrons by the stabilization energy corresponding to the movement of those orbitals. And you see that you've got minus 1.2 plus 1.2, and that gives you a 0. So it means there is essentially no crystal field stabilization energy associated with the manganese 2 plus in this one. So it doesn't have preference for a specific site. It's going to be forced to be there in any case. So if you go to the second component of the spinel, the 3 plus oxidation state, manganese being D7, the charge of 3 plus leaves 4 D electrons, and distributing this into the T2G and EG, there will be 3 electrons, similar to the question one of you asked about it, that you don't understand why a D4 in one case goes to a T2G3 and an EG1 and a T2G4 and a 0. That is because in one case, the delta O was too large. So here we're looking at a situation, minerals where the oxides are the ligands, and as a result, replaced with the sulfides. In some cases, a lot of minerals, those who will be doing projects with maybe Prof. Chauke in physics will be doing pentlandites and all compounds that contain, similar compounds that contain sulfur instead of oxygen. But now D4 distributed like that, you multiply each by the stabilization energy, that gives you minus 0.6 delta O. So you can see that the 2 plus, 3 plus oxidation state is really stabilized by crystal field stabilization energy. Its energy is 0.6 being exothermic, if you like. In the 2 dimensions, I think you're looking at the sign to choose whether process is really favorable or not. That so essentially, we're seeing that the MM3 plus is more stabilized because it has, the other one has a 0. So as a result, and you don't have to argue this mathematically to say that, oh, on the number line, a 0 would be larger than minus 0.6. We're looking at the energetics here. So the energy that is expended really tells you that you're resulting with a stable system, because energy destabilizes system. So you've got the 3 plus oxidation state being very stable in the octahedral environment than the 2 plus oxidation state. And as a result, from our definition, this would be a normal spinel, because you have got a high charge being stabilized in an octahedral environment. So this is one of the examples where you're seeing the direct application of the crystal field theory in deducing whether spinels would behave magnetically, non-magnetically, or whatever. So that's very important. Let's go to the second example and look at the spinel magnetite or magnetic iron, which is Fe3O4. You've got Fe or iron monooxide, which is FeO, and hematite Fe2O3 as components of this spinel. So in the hematite, the iron is in a 3+ oxidation state. In wustite or Fe0, it has a 2+ oxidation state. So you're doing exactly what you did with the spinel case, that you look at an oxide, supposing you just do the calculation once. Some people can do calculations in both the octahedral and tetrahedral. That's time wasting, because you can easily deduce from doing a single calculation, considering a single coordination environment. So you've got Fe2, iron is a D8 metal. The 2+ oxidation state leaves 6d electrons. And the 6d electrons in an octahedral environment of weak field ligands will definitely give you a T2G4 and an EG2, because electrons will occupy all the d or the splitted orbitals, both the T2G and the EG. Before they start pairing, 5 electrons will go into that system, and then the 6th one will pair in the T2G, and you remain with the T2G4 and the EG2 electron configuration for that specific ion. And then if you do the energetics calculation by considering how many are stabilized and how many are destabilized, you're ending up with minus 0.4, because you've got 0.4 times 4 giving you minus 1.6, and you've got 0.2 multiplied by 2 giving you 1.2. So you can see there's a deficit of 4 in that case, and the sum is actually minus 0.4. So you now consider the next component. You don't just do the calculation for one, and you cannot do it to see if otherwise is stable or not in that particular environment or coordination environment. The Fe2+, 3+, the trivial case, because you've got all the electrons now occupying both the T2G and the EG, and its equal occupations. The stabilization equals destabilization, and you're ending up with 0. So there is 0 stabilization, which means that it's a trivial case, but that 2+, that is your metal in a 2+ oxidation state, is stabilized by the crystal field stabilization energy in it. So now you have an Fe2 having a larger, if you like. I said, don't worry about the sign here. The sign just tells you that energy has been expanded, and as a result, the system that you have would be stable, because the reverse is otherwise. So now you've got a metal ion in a 2+ oxidation state that is more stable in an octahedral field than its 3+ counterpart. And as a result, such a spinel would be an inverse spinel. So magnetite is an inverse spinel, given this calculation over here, or given the amount of energy. And in real life, you're finding that as well. So I would like you to just practice what I have done and go back to the issue of the octahedral site stabilization energy that I spoke about. Some people would call it the octahedral site preference energy, that the metal ions would prefer to reside more in the octahedral sites than depending on the amount of that energy. So the octahedral site stabilization energy is really a way on energetic of favoring the octahedron rather than the octahedron. So please do that and work through the examples here. The exercises that I have for you here, I think some of them I just checked whether students really question things or practice examples. There are previous examination papers that have got these spinels here as questions. So if someone had done them after the class, I think the chance of getting full marks on this is very high. And the tip here that you have is that if you've got the tetrahedrali coordinated metal ion being a D6 up to D9 ion, and B the 3+ oxidation site in your octahedron being Fe3+, then the spinel is always inverse. And I think, and asked why, I'm not sure if many of you will be able to, but you can understand that and answer this question by please considering Fe3+ minus what do you have on Fe3+? which is a D5. We spoke about it in the magnetite case. So I'm not going to go into that. So it's a tip that I want you to use in answering questions. But very often, I think even your year-end question paper would need you to classify using crystal field theoretical calculations, which is your crystal field stabilization energy, to say you've got an inverse or a normal spinel. So I would like just to look at certain electron configurations that are really unique. They are a class of their own. This is why the slides are titled special case 1, special case 2, and special case whatever. So there are those electron configurations or d electron configurations that are not susceptible to the ligand field strength. In other words, if you look at them, if you consider a strong field case where the ligands are all strong field and they cause large splittings, it will give you a specific T2G, EG configuration. And if you take the weak field case, you're arriving at exactly the same. So in this case, we say these electron configurations, I can say they are insensitive to the strength of the ligand. The first example is a D8. In a strong field case, or let's start by a weak field case, you've got 8 electrons to put in the T2G and EG, right? If it's a weak field, then electron can access the EG set of orbitals without carrying. So you've got 3 electrons going in there and 2 going in there. So you've taken care of 5 electrons at once, distributed nicely, singly with parallel spins in both the T2G and the EG. And that leaves you with 3 electrons. And the 3 electrons will now have to occupy low energy orbitals until they are complete. So you don't have any more electrons. Then you've got an electron configuration T2G6 and EG2. And if you consider a strong field ligand, in a strong field ligand, the splitting energy is so large, electrons prefer to pair before they can go to the EG. So you've got 8 electrons, you're taking the first electron to occupy here. It's going to be 1, 2, 3, right? Now they are all happy according to Jahn's rule. But then the amount of energy that is needed to go there is large. So electrons energetically, from a thermodynamics point of view, electrons now pair until there's no space in the T2G. So you've taken care of 6 electrons, you are left with 2. The 2 electrons, when they go up there or to the vacant rooms that are available, they find that they are equal in energy. So they will occupy them one by one. Very important. That is your application of the Jahn's rule. And this involves the application of both Jahn's rule and Pauli's exclusion principle, that 2 electrons in the same orbital must phase in different directions, or must spin in different directions. So the configuration that you're finding in a strong field case is the same as that you're finding. So this is a special case. But all the other DN configurations are susceptible to strong field, weak field. Right. So we must take care of that. But now we see very important consequences coming up as a result of the occupancy that we've seen. The insensitivity has got some other addenda, if you like. If you look at the T2G, it's very happy, completely filled. So if you want to participate in any interaction or in any reaction, if you like, it's like a noble gas. You've got a noble gas configuration, if you like, here, because it's a closed shell. But going up there, you've got a single electron in each of the orbitals. And now I would like us to revisit the shape of an octahedron in order to allow to enable understanding of what is happening here. And because of my poor computing skills, I had to use someone's figure. The plot that you're having here with beautiful electrons, blue electrons going up, going down, hasn't been drawn by me. It's beyond my computer skills. So it was drawn by someone and given to me as a hard thing that I cannot manage, I cannot fiddle with. And the idea is correct, but if you look at the values that we have here, have been swapped. We have got a single electron in the dz squared orbital, which is the orbital along the z-axis, and we've got a single electron in that four-lobed orbital that spans the x and the y-axis. Definitely, the dx squared minus y squared orbital is the one that interacts with four ligands, not the other. If you look at the explanation that this guy has put, please keep track of that. I would like you to have your printed slides and change the designation that we have here. It is the electron in the dx squared minus y squared that is repelled by four ligands, not two. But on the z-axis, in an octahedron has got four ligands in the equatorial plane, and it has got two ligands in the axial plane. So that must be 2, and this must be 4. Please do me that favor, and let's understand the argument of, or the consequence of this splitting pattern that's going to happen as a result of the special configuration. It's not induced by the ligands as such, because both strong field and weak field case give the same result. So the thing is now, having single electrons, this one being repelled by 4 electrons, and the other one being repelled by, is the same, 1 electron in each case repelled. So you can see that the repulsions that are exercised by 4 ligands on that electron will be more than the repulsions that are exercised by 2 ligands on that electron. And as a result, that will break up the degeneracy of, because of the differences in the amounts of, or the total amount of repulsions that are happening in specific directions. The EG set of orbitals will split because of the differences in the repulsive influences induced by the ligands in that direction. And as a result, the 4 ligands will repel this largely enough, and as a result, you see the dx squared minus y squared orbital going up in energy, or being elevated in energy. If you look at this diagram to the left-hand side, which is just the same as the one on the right-hand side is actually the end result, if you like. So essentially, because of significant repulsions in the xy direction, this orbital will be elevated in energy, and because of the relatively smaller amount of repulsion that electron suffers, that orbital will be lowered in energy. And when that breakdown in the degeneracy happens, the electrons cannot prefer to be singly or to occupy singly in orbitals of different energy. They will all share up or pair up in a low energy orbital and leave the other one vacant. It's a very important consequence here. So this first portion here is concentrating only on the EG set, which is what you have there. What I'm trying to say, right? You look at this situation here. Right. I think I've clarified the mix in the numbers there. So this is your EG set. It's we looked at the splitting in that direction. So that's fine. We now have the dz squared orbital being less repelled because it is confined to two ligands. So it goes down, and you've got a pair of electrons happening in there. That is partially just by direct consideration of that. But if we look at what has happened, we have got orbitals. The elevation of that dx squared minus y squared is definitely because these are vectors. The orbitals are put on the Cartesian. The dx squared minus y squared orbital being elevated in energy means that in the lower set, those orbitals that have got an xy component will equally be elevated in energy, will be more affected by the ligands. And as a result, or those orbitals that have got a z-axis will be lowered in energy from the T to G set. We don't keep the T to G as being degenerate because of this loss of equality in the orbital sets. Then we've got a splitting that happens in the EG and happening also in the T2G. So all the T2G orbitals with a Z component will be lowered in energy. You can see them transforming as the dxz and the dyz. If you look at the bottom part of this diagram here. So they transform as a degenerate set. The one that has got the XY plane or XY components, just resolving your vectors into components, I think you know what's going to happen in that case. Those who are doing or who have done physics 1 will remember this, or who have done applied maths will remember this. So definitely, you now have the orbitals that have got an XY component being elevated in energy. And essentially, the splitting pattern that we're resulting with here is typical of what is called a square planar complex. Because in a square planar complex, the ligands along the z-axis, if you like, you've got ligands being arranged towards or at the corners of a square relative to the central metal. The metal sits at the center, and you have got a geometrical figure called a square, where now the ligands are occupying. And the square has got all sides equal, all the diagonals equal, so you can see how symmetric that's going to be. Such a compound that has got 4 ligands at the corners of a square is called a square, and it's planar because it can lie flat like a book on your desk. It's a square planar a coordination environment, if you like. So if you're pulling out the X ligands, I mean the Z ligands, you're remaining only from an octahedron if you do that. And what I'm saying here is going to be a subject of the distortion in the next couple of slides that we'll be looking at the distortions from the geometrical, octahedral geometry. So essentially what we're doing in this case, if you're pulling out, you just imagine, because you can't handle this molecule with your hands, but ideally, knowing that you've got 2 ligands in the Z direction and 4 ligands in the XY plane or in the equatorial plane of your molecule, imagine yourself handling the molecule by the bottom ligand that is along the axis. In fact, the nomenclature of equatorial and axial is coming from your geography, from the globe, that the Earth is a spherical object and it's rotating on its axis like that. So, and half between the top and the bottom is the line of latitude called the equator. So the equator cuts the globe into 2 halves. So if you look at the geometry of the octahedral complex, the 4 ligands are arranged along the equator, if you are going to liken it to the Earth as a globe. So they are going to be along the equator, and those 2, the last 2, the Z ones, will be along the axis on which the Earth is rotating as it exchanges day and night. So that is a very useful interpretation and nomenclature in both from your first year in any case. So this is very important. Imagine yourself pulling out the ligands along the Z-axis. If you pull them out of the metal center, you're increasing the distance between the metal center and those particular ligands. So the interaction decreases. Remember, this is Coulombic, if you like. The force would vary with the square of the distance, the inverse of the square of the distance between them. So as you pull the ligands out, the influence or the energetics, this is why you're seeing the Z component or the Z orbitals going down in energy. They are less repelled now because the ligands are being drawn out. And as you continue drawing them out, at some point they will tear off from the metal, and you will remain with 4 ligands that were in the equatorial plane. And that constitutes your square planar complex. Please visualize that correctly, and let us see the next special case before we look at the distortions, because this is one example of the distortion, but this doesn't really result in a distorted molecule. The second special case here has been termed a Jahn-teller distortion, because it was essentially firstly observed by these 2 physicists here, that really we saw that in an octahedral complex, the orbitals will be splitted into the T2G and the EG set. And it can happen that in the previous case, you've seen that the EG orbitals can be equally filled. So if they are equally occupied, it means the repulsions between the ligands can be the same, if you like, and that defines a regular octahedron. Not regular in the sense of coming to class every day, but regular in the sense that all the sides are equal, all the phases. Remember, an octahedron has got 8 phases. The name octahedron means that you've got 8 equilateral triangles that are building up there. You've got 4 of them from the equatorial plane, or from the center of the molecule. If you're taking the metal ion as your reference point, you'll have 4 equilateral triangles having an apex, defining a pyramid, if you like. And you've got 4 others defining another pyramid at the bottom of the figure. So that is how an octahedron looks like. And very importantly, in a case where you've got equal occupancies in these degenerates, because very importantly, I don't know whether you've realized that, in an octahedral complex, the orbitals that are used to attach the 6 ligands are the ones classified as the EG. That is the dx squared minus y squared, taking care of 4 ligands, and the dz squared taking care of 2 ligands. So all the 6 ligands are essentially attaching on those orbitals. So they really dictate the shape of the resulting octahedron. So if they are equally occupied, you're having a symmetric figure with equal size, if you like. Right? But now what happens if the occupation in these orbitals that are used to being, they're so used, they like being degenerate, equal in energy. Now, if one gets more electrons than the other one starts toying and marching, going to Pretoria, right? Because they essentially deserve equal, by the mere considering of their degeneracy, they deserve equal populations of electrons. So what if the electron configuration allows one of those 2 to be populated? The consequences are to be seen as we look at the diagram that is pasted on there. That you know that normally you've got unperturbed d orbitals that appear as a set, that's fine. But under an octahedral ligand field, you've got the T2G coming through and the EG coming through. So you've got another special case here is your D9 or 9 electrons in the D subshell. That's typical. In fact, in your book, I think you'll find more emphasis on copper 2 complexes. And I think you may have realized that in your second year course as well, of the special nature of the D9. But let's look at it in the context of the crystal field theory. This is one more electron than the previous case where we looked at the D8 and we found that the 2 orbitals can be symmetrically filled. But now there's one more electron. The D9 has 1 electron. 1 electron can either, it has got a choice, because you'll start populating this with a single electron at a time. But the 9th electron will either have to pair with that electron or this. It doesn't mean that it has to automatically go there. Right? So that equality now, or that politic type of approach is coming through here. That this orbital will say, why this guy, we were born at the same age, at the same hospital, at the same time, and now this guy gets more than what I have to get. No, something is wrong. And same thing applies. If this one goes there, so we say this is a degenerate electronic configuration. That electron configuration can be written in 2 forms, if you like. It can be written as it is here, with the dx squared minus y squared having 2 electrons in them, and the dz squared having 1 electron as such. Okay, so there must be 1. I prefer writing 1. Okay, but you can see them. Okay, right. You've got that 1 electron in the dz, but the alternative, equally correct electron configuration will be the dz with 2, and the dx squared minus y squared carrying 1. So it's actually the same configuration. If you have to write it in T2G, EG, whatever, the EG will still be EG3. Whether you've put an electron in the dx squared minus y squared orbital, or you've put it in the dz squared minus orbital, It's really immaterial. But it has got dire consequences. Right? It has got dire consequences. And we're seeing now this guy had sobered up in this one here, that really there are 4 ligands that are repelled, and there are 2 ligands that repel it. And essentially, this has consequences of which of the 2 configurations to adopt. If you look below this, I've written them out here, that you can have 1 electron in the dz squared orbital. That's equally correct. And you can have 2 going there. But you can also have 2 going in there and 1 going. So the ligands will be repelled by, no. So in this case, 2 ligands will be repelled by 2 ligands. And, 2 electrons, let me say that. And the 4 ligands will be repelled by 1. You can see the dissymmetry coming out there. Okay. In this case here, 2 electrons are repelling 4 ligands, and 1 is repelling that. Definitely, this constitutes now a dissimilarity, similar to what we have seen. And we see the elongation. If we have got too much electron density in this, as it is here, electron density would be concentrated in the XY plane. And as a result, the ligands that are in those directions will be repelled farther out of the complex. And as they are repelled farther out of the complex, the axial ligands would find a chance of coming closer to the metal. We will now end up with an octahedron that is no longer regular. We talked about, or I introduced the concept of a regular octahedron. But now, regularity gets lost. If you start looking at the observation, or because of the electron population, the observations that you have here really deviates from a normal octahedron, because the more electrons you have in the XY plane would elongate the bonds in that direction. So you're ending up with a deflated octahedron, with the Z ligands coming closer to the metal, and so you've got it's sort of oblate, if you like. But if you've got a high population of electrons in the Z squared orbital or along the Z axis, it means that now the ligands in the Z direction will suffer significant repulsion, and their bonds will elongate, and those in the XY plane would now find a chance of coming closer, because as those ones move out, they're decreasing electron density at the metals, and the other ligands come up, find a chance to come up, because ligands by themselves. So if those ones generate room, these ones come in. So you can see that either case, whether the odd electron goes into here or in there, it causes some sort of a distortion. It elongates certain bonds and contracts certain bonds. That is very important consequence that is covered in what is called the Jahn-teller theorem, which is what I think would come up in this. And I would like you to just, that in any nonlinear molecule that is in an electronically degenerate state, an electronically degenerate state is what I was talking about in the previous slide, to say that you can write that electron configuration in 2 forms, because the extra electron can either go into the dx squared minus y squared orbital, or it can go into the dz squared orbital. So that is electronically degenerate. The electron has got a choice of going into one of them, and as a result, such a system is unstable. It cannot retain an octahedral coordination, but would minimize the energy by distorting. So it undergoes a distortion to form a system of lower symmetry. And really, I said, if the electron or electron density or 2 electrons are in the XY plane, you've got elongation in the XY plane and contracting in the Z plane. So you're losing your regular octahedron. The sides are no longer equal, or the bond lengths are no longer equal, because in a regular octahedron, all the bond lengths should be the same from the metal center to any of the ligands. It should be the same distance. But when you start having this dissymmetric occupation, you've got some bonds elongated at the expense of the others. And as a result, the octahedron loses its regularity, and we say is distorted. So what we have seen in the previous slide can be summarized by the diagram that is on the left-hand side of this diagram here. that there's going to be a degeneracy of the orbitals is removed by unsymmetrical occupation. The electrons are the orbitals are intrinsically degenerate. And now you start populating them with different amounts of electrons, and that political glitch breaks up the degeneracy, with one being lowered in energy and the other one being elevated. Essentially, due to the electron configurations that I've written at the bottom of the previous slide, you can see the z-axis being, this is when you've got repulsion now in the xy plane. Then you've got longer bonds because of the repulsion. So that leaves the dx squared minus y squared at the top there, and the dz squared being lowered in energy. But remember, we said that when a distortion happens in the xy plane, those orbitals that have got similar components in the T2G will also undergo a split. As the dx squared minus y squared increases in energy, the dxy, it's a related, it's an orbital that has got the same components, if you like. And you may realize, if you like, just play, or draw them on a piece of paper. And after drawing the the dx squared minus y squared orbital, draw another figure to designate the dxy orbital. You'll see the dxy will have their lobes pointing along, say, the line y is equal to x. Those who are doing maths would have done mirror images and what. So you will see that really symmetry plays a role here. So this has got the y component, they are elevating energy. Now here, if the ligands, if the two electrons are in the z orbital, the z squared orbital, ligands in the z direction are repelled. So the repulsions are high, and you see the orbitals going high in energy. And as they go up, the other ones will come in. That is why you see the dx squared minus y squared going down in energy. So any orbital in the T2G set that has got a z component is going to undergo an increase in energy. That is why now the degeneracy is broken both in the T2G and in the EG sets as a result of this unsymmetrical occupation of degenerate orbitals, or orbitals that are naturally having the same energy. They should be treated alike. If you give one 5 rands, you must give the other one 5 rands. Otherwise, right? So this is essentially a very key point, and it's very useful in understanding the electronic spectra of transition metals. It is a very, very important observation, and something that you should know throughout, particularly those who like to go into research labs, and those who would like to take the honors course. They will be doing electronic spectroscopy, and they will see what feature comes up as an addendum compared to what you naturally expect because of the distortion. So that's very important, that a distortion can happen. Look, this figure here is essentially showing you the distortions relative to a regular octahedron. In the middle here, you've got the splitting that takes place in a regular octahedron with similar size, or equal size, if you like, the T2G and the EG separated by 10 dq or delta O. But immediately you start having that unsymmetrical occupation, particularly say with the D9 having an extra electron in one of the orbitals, you definitely have splitting happening relative to the original conformation. And as a result, you see that you can essentially still work out the dq, the 10 dq or delta O, because if you take the distance from this x squared minus y squared to the xy, you will find the same value as what you have. And if you take the measurement from the degeneracy of this, from xz, dxz, and the dyz, and you go to the dz squared orbital, you'll find the same distance. So you can essentially be able to work out your delta O even in a distorted octahedron, an octahedron that has got similar bond length. Right. So I hope I was able to catch your attention on that. So these are essentially the shortcomings of the crystal field theory, which I think by reading through you have got to understand them. But the major weakness of the key of the crystal field theory is what we have seen as the order of the ligands, which we refer to as the spectrochemical series. That relative to the basic assumption of the crystal field theory, which is electrostatics. There is no way we could expect that n-ionic ligands should be weak field ligands, because we expect a positive charge to like a negative charge. So those negatively charged electrons were supposed to be at the top of the series, but unfortunately, experiments have proved that they are weaker ligands than many other ligands. And that is the first key point. The other important point that marks the difference is that particularly that reasons out why the spectrochemical series is relative to the expectation is because we're totally ignoring covalency in the bonding between, or this theory totally ignores covalency. It assumes that the bond between a metal and an electron is ionic, which is definitely not the case. That's why we're seeing that anomaly happening in the spectrochemical series. And as a result, we would be able to see actually what was supposed to have been done when we look at what is called the molecular orbital theory, which is a subject of what is called the ligand field theory. The ligand field theory is essentially the same theory that we've learned. It's the crystal field theory, but now takes into account covalent interactions that are happening between the metal and the ligand. And that will allow us to rationalize the order of the ligands as we're seeing them in the spectrochemical series. So we'll get that in the next lecture, I suppose, but I would like you to look at why the shortcomings really are important. If you look at the spectrochemical series, n-ionic ligands are at the bottom. That wasn't supposed to be expected from ionicity. You've got ammonia or NH3 being a stronger ligand than water or H2O. If you look at the periodic table, I mean, we're looking at ions, ligands as ions or ligands as dipoles. So if you look at the position of the donor atoms in these two ligands here, ammonia donates through nitrogen, and H2O donates and attaches to the metal through oxygen. And if you look at the periodic table, oxygen is to the right of nitrogen, which means oxygen is more electronegative. And as a result, the most electronegative atom was supposed to interact with transition metals significantly. But that is not the case, right? So that is one of the anomalies, and they are explained by the ligand field theory. The other important observation is that if you look at the spectrochemical series, you will see water being a neutral molecule, but being a stronger ligand or being found to the right of the hydroxide, which is an n-ionic ligand. We expect n-ionic ligands to split the d orbitals to a larger degree than the neutral ligands, but that is not the case. So